Hello, my name is Ana González, and I'm Director of Strategic Partnerships at iPronics, and I'm going to talk about iPronics and the technology that we developed that is based on silicon photonics. Also, I'm going to talk about our first product, the iPronics SmartLight processor, and about how we are approaching to the market. So we think that adding programmability to silicon photonics is the natural evolution that will enable silicon photonics to be commercialized for other applications different from the typical transceivers. I would like to start stressing what happens when you add programmability to silicon photonics. So first, you go from having a static solution to have one dynamic solution that can adapt to new needs of the network without changing the hardware, but just by reprogramming. Also, you have a device where multiple tasks can happen at the same time. So you can have a filter to remove phase noise together with another filter to compensate dispersion, and then a coherent mixer just in one device. Also, it's a smart device that can optimize itself. And in addition, it has the capacity to increase tolerances for the fabrication process. This is a sketch of the iPronics SmartLight chip. It consists in a hexagonal mesh of Mach-Zehnder interferometers. Each side of the hexagon is a tunable element, and we can control light to go in a specific way using thermo-optical phase shifters. So we can do interconnects, beam splitters, variable optical attenuators, filters, and matrix multiplications. You can switch between these functions in question of milliseconds, and you can have different parallel processes at the same time. Also, at each optical port, we have a monitoring photodetector. And then, as the monitoring unit can talk with the driving unit, the device can optimize itself. And, for example, it will be very useful to compensate for real-time fluctuations of the network. Last point that I would like to stress is how programmability relates to an increase in the maturity of silicon photonics fabrication. So we have heard many times like silicon photonics is not good enough for doing filters because, you design a filter like this one that we have here with a central wavelength in the 1550, an excitation ratio higher than 30 dBs, an insertion loss of 2 dBs, a free spectral range of 2 nanometers. And yes, you design this, you send to the foundry, and when you get the chip back, this is what you have. So the central wavelength is not where you wanted it to be, the extinction ratio is not that high. So then what happens when we use programmable photonics for developing the same filter that we did before? Well, it's not that the foundry fabricates better for us, right? However, because SmartLight works by software, we can adjust the coupling factors and tune the central wavelength and the extinction ratio, and suddenly the fabrication process of the foundry is mature enough for developing filters and any kind of function, independently of the low tolerances for small deviations in the fabrication process. This brings me to the point that I wanted to make. The software is the key component in the development in this development. In our case, we use a Python-based software that enables to reprogram the device in seconds. It allows the calibration of each tunable element, and also we have developed automated functions, but also the user can work in full design environment. And in addition, we have a simulation tool that is intended for product development. First problem that we have decided to address is about reducing the barriers associated to the development of new products based on silicon photonics. These barriers are related to the risk of missing the market windows opportunity for a particular product because of the long time of silicon photonics development cycle. For this, we developed our first product, the SmartLight processor. It's a laboratory device. It allows you to generate photonic functions in question of minutes or days if it's required a lot of programming. Its use is intended for including the system in prototypes that require a photonic function before going to production. To reach that point, the company started in 2019, obtaining an ERC proof of concept grant to demonstrate the technology and to develop the first prototype. And last year, we got 2.5 million from an EIC transition grant and 3.7 million with the first private funding round. We got several awards, to highlight here the Nature Research Award, and we have some landmark articles such as this one here, published in Nature, and our technology is well protected through patents. Finally, I would like to present our management team that mixes scientific excellence and business development expertise. And so far, we are around 52 people in iPronics, and we benefit from our founding partner, that is the University Politécnica de Valencia, and we have a strong track record of achieving our goals. In conclusion, we are a highly motivated and strong team, and I have no doubt that we will succeed in bringing programmable photonics to all levels of industry across different applications. And that's it. Thank you very much for listening until the end, and see you at Photonic West.